Let's talk about bracketing a maximum. So the setup of the problem. We've got some interval from x1 to x4, and we know that there exists exactly one maximum between them. If we don't know that, then we can't really improve our brackets. We have to start with the idea that to bracket it, we have points on either side of the maximum, and we know there's only one maximum between them. In this sense, it's the same as when we're trying to find roots. We have to have just one root that it's in between the 2 points. We have to have the correct initial guess that brackets the maximum. So when we've got that, then what we want to do is gradually make this interval smaller while guaranteeing that the maximum still stays inside this interval. Now with roots, it was relatively straightforward. We picked one point and then we determined on which side of that point the root fell. And then we could eliminate the other side and continue from there. All we need to do is check whether the function value changed as it went through that point. Turns out with determining the brackets for a maximum, it's a little bit harder. In this case, we want to know, is it on this side or is it on the other side? It turns out with roots, we can go ahead and do that in a straightforward manner, but with brackets, we can't. So what we want to do is show why this is not the case. So let's say the curve looks like this. In this case, we certainly have one maximum in between. It starts at f of x1, goes through f of x2, and f of x4. However, with the same 3 points, we could draw another curve where the maximum is in the first area. This goes through all the same 3 points, but the maximum is now in a different subinterval. We can change the value of f of x to any direction we want to, and we'll discover the same thing. We can still draw curves that satisfy those 3 points, but that have maxima in the different subintervals. So we need to do something different if we want to bracket a maximum than we did with a root. Turns out what we need to bracket a maximum is 2 points in the middle instead of just 1. So we've got our same interval now, and now we've got 2 points. So now, if we've got 2 points, what criteria can we use to decide which of the subintervals it's in? We're going to be deciding between the interval x1 to x3 and the interval x2 to x4. So this way, we've got our 4 points and decide which 3 of them will bracket the root. Then we can introduce new points in that new subinterval and continue the process. So this is the process we're trying to decide. Is the maximum in the x1 to x3 interval or the x2 to x4 interval? Well, it turns out that if f of x3 is greater than f of x2, the maximum must be between x2 and x4. We don't use any other information about the function values, just that the function value at x3 is greater than the function value at x4. So let's see what that would look like. There we've got a curve that's going in between, and certainly this is consistent with the idea that the maximum is in the second interval when f of x3 is greater than f of x2. So it certainly makes sense. The question is, does it have to be this way? Well, let's try to draw a curve that violates this. So now here we've got a curve. It goes through all of the points, so that it satisfies that. F of x3 is greater than f of x2, but it has a maximum between x1 and x2. The maximum is not in the red interval. Now the problem with this is that there's now 2 maxima. But we'd start out saying, no, in this bracket, we only have one maximum. So in order for the maximum to be between x1 and x2, and for f of x3 still to be greater than f of x2, then therefore there'd have to be 2 local maxima in this interval, which is not the case. We said we had to have it bracketed, so there's a contradiction there. Either we didn't actually bracket it, or f of x3 is not greater than f of x2. We've shown that if f of x3 is greater than f of x2, the maxima must be in that second interval, the interval that contains the larger number. So let's turn it around and look at the other situation, where f of x2 is greater than f of x3. And what we'll find, as makes sense, is that if f of x2 is greater than f of x3, the maximum is between x1 and x3. This is, by symmetry, pretty much the same thing. Here again, we're saying that the maximum has to be in the interval that has the larger value of the function. So the curve would have to look something like this. We don't know where in that interval where it is. If the curve changes a lot, then that maximum really could be anywhere in that interval, but it has to be in that interval. So let's try to draw a curve that doesn't have the maximum in that interval. Again, here's a curve that we've drawn. The maximum is between x3 and x4, and f of x2 is greater than f of x3. So this violates that. F of x2 is greater than f of x3, but the maximum is not in that red region. But again, it has 2 maxima in this region. So these are our choices. You could actually have the other case where f of x2 is equal to f of x3. It turns out if that's the case, that the maximum has to be between x2 and x3, but you usually don't find that's the case unless it's a very special function and you choose your positions exactly right. But in that case, if it's between x2 and x3, then it actually falls in either of the two intervals. So even if f of x2 is equal to x3, if you don't take that into account, it'll still be in either one of the intervals that you've selected. So there we go. That's how we bracket a maximum. Notice it doesn't matter how you choose the x2 and x3. So this works the same for parabolic interpolation. It works the same for golden ratio search, any way you want to do it. So practice a little, draw some cases, think about it a little more, because it's a little harder than bracketing a root. Again, this is the same procedure. If you've got it bracketed, you just follow these rules and you will get, eventually as you keep on cutting down and cutting down, you'll have your maximum to whatever arbitrary error that you want. Again, the same thing applies to minima. We could turn it around, and there our greater than signs will switch to less than signs switch to greater than signs, because there we'll be looking for which one is the smallest. The minima will be in the interval that contains the smallest function value.